All right, so a gentleman wrote to me about the quality of the videos, and I agree. It's a low budget production right here. So the calculus lessons, 1 to probably 40 or 50, are just there to get students some practice. The explanations as to why things work are probably in more detail in the playlist. I would suggest you go there. I think those are there's 5 or 6 videos that I don't think you're going to see elsewhere. Using zeros and ones to write graphs quickly, I think should be something you start at the Algebra 1 level to help understand the conversion process. Students have a very difficult time with understanding what a radian is when they get to trig. I think you got to start looking at that much sooner, and there's a good video on the playlist on that I think can help you. I think maybe the most important one out there is putting cubics in graphing form and the geometric method of completing the cube. And really, I think most of high school math comes from rectangles. So, you know, those first 50 lesson sets from Algebra 1 to Calc are designed to get enough of a foundational practice to just get some conceptual awareness and some skill. And the only thing I know about skill is it takes a lot of repetition. So if you've noticed, we're doing a lot of repetition. Is it the same experience as being in a classroom at the board? No, but it's best I can do. I've got 50 years of being a math teacher, and I don't know what I was doing for my first 15 because I certainly wasn't a math major, but I did keep an eye on what am I doing and where's it coming from. And God, it took me 45 years to make the connection that completing the cube is just a step up from completing the square. And if you haven't seen it done geometrically, I think the most important part of learning algebra is its geometric underpinnings. So I strongly suggest you take a look at some of that. Now, what I'll try to do is keep this camera closer to the board here. And I did put a blurb in that I will just copy and paste on every calculus lesson set now, saying what I just basically talked about. All right, so that's a ramble. Let's just do some calculus. And we started with a problem in lesson 10 that I should have probably done first here, but it's at the end of the lesson set. And that's looking at derivatives from a graphical perspective. All right, so now we're just going to do quick 12 problems here that should be repetitive from previous lesson sets. Shouldn't have to spend a lot of time on them. Maybe you can do most of them in your head. So you've got acceleration, velocity, position, and position is the parent function. Its derivative is velocity. That's what changes your position if you're driving a car. Is, you know, all right, speeding up, slowing down, and that's acceleration, and that's what I'm giving you, 4t plus 3. And I want velocity. So velocity is the integration of acceleration. So velocity, in this case, it's going to be 2t squared plus 3t plus c. And when we put a 0 in, we want c to be 5. So we can write 5. I might as well do position. I didn't ask it on this worksheet. That would be t to the 3 over 3 times 2 plus 3t squared over 2 plus 5t. And I didn't give you an initial condition. That's an initial condition. I didn't give you one. So you'd have to write C. Problem 1 is in the books. Problem 2. Can you write the derivative of 1 over x cubed? Well, you got to know you can write that as x to the minus 3. What's the derivative of x to the minus 3? Minus 3x to the minus 4. Dropping down 1. Okay, so those two are done. Now we got quotient rule. I hope you've got that down now. Low d high minus high d low over low low. So we got low. So y prime is equal to low x cubed minus derivative of high, which is itself, times the derivative of the sine of x, which is cosine x, minus high, which is e to the sine x, times the derivative of low. The derivative of x cubed is times 3x squared over low low, which is squaring, low squaring x cubed. Just trying to put the quotient rule into your longer memory banks by doing it again every lesson set. All right, how do we approximate the cube root of 125.1? We did a cube root in the last lesson set. I said I think it looks like that. Over here it's pretty flat, and a cube root of 125 gets us 5. So the equation of the tangent line can start with x minus 125 plus 5, and now we need the slope. It looks like I'm not going up very fast, so I need the derivative of the cube root at 125. So I'm going to go to x to the 1/3, that's the cube root, so its derivative is 1/3 x to the minus 2/3. Yeah. So I'm going to drop 125 in. Cube root of 125 is 5. To the minus 2 is 1 over 25 times 1/3, 1 over 75. And when I drop 125.1 in, I get a tenth. 1/10 times 175 is 1 over 750. And I need to put the 5 in front of that, and that's a darn good approximation for the cube root of 125.1. Could have done that in your head. Didn't have to even write it out. All right. Next one, x squared plus y squared equals 25. We've got a little implicit differentiation that we've done several times. This particular problem, it's a circle at -3, -4. -3 about there, -4 about there. We're looking for that equation of that tangent line. Looks like my slope is negative, but let's go get it. So we got 2x dx. I'll write this out because it won't take too long to write that out. 2y dy equals 0. Let's divide by 2. Get the 2's out of here. And now let's divide by dx. Right? And pretty soon we're not going to be talking about that anymore because it disappears. But there's what we're looking for. It's in the problem now. Of course, dividing this by dx is still 0, yes. All right, so how do I isolate dy dx? I got to move the positive x to the other side. And then I got a multiplication becomes division. And I'm at the coordinate -3, -4. So the opposite of -3 is +3 over -4 is -3/4. Does it look like this slope might be -3/4? I hope that's believable. All right, so I think we can see that a little bit better than the previous video. So I think I'm in a little better position and can get away with this, I hope. And now, instead of moving the computer, I'll move the board because I think I'm in a pretty decent place to see the work and talk about the problems. Repetition is my friend. I'm hoping I'm sorting out the problems with making these videos so that if somebody's really well motivated, they have an opportunity to do some math. All right, so you're looking at number 6. The limit as x goes to 0. Remember, you're pausing the video. I'm just going on. What do I see? I see a sign change here. I see a sign change. If I put in -0.001 or if I put in positive +0.001, I'm getting very different answers. When I put negative in, this critter's going to -infinity. Put that small number into 3. Should be able to understand that. Put this small number into 3 and I'm positive infinity. They're not going the same place, so we say does not exist. Now, if I came in from the right, that's what that means. That means I'm just looking at the positive. Then I would say that this critter goes to positive infinity. Okay? Now, if that's the first time you've done one of these lesson sets, then well and good. A conversation has started. And this is fuzzy down here. Don't know why. All right. I kind of wish I had my old computer. But they can do here. I didn't know. I'm a dinosaur. I don't have much technological expertise. Which is why when the graphing calculators came out, I said, well, if that can graph, you know, a logarithmic equation, let's say x equals 5, and it can do a 7 gets us 11, and a 15 gets us 22. If calculator can get that graph quickly, then we should be able to too. Let's make that 23. So 11 plus 12, it's a logarithm with x equals 5 as an asymptote. And if I go to 7, I've changed by 2. If I put 15 in, 10 divided by 2 is another 5, so let's make this 16. 7 to 16 is 9 units of change. I'm sorry, from 5 to 16 is 11 units of change. So when I drop 16 in, I get 11 halves. That can become the base of this exponential function. All right, so 5, domain restriction is done. 7 minus 5 is 2. 2 divided by 2 is 1. Log 1 is 0. That gets me 11. 16 minus 5, 11 halves. What do you put on top of 11 halves? You get 11 halves, 1. 12 and 11, 23. So that all started for me in the late 80s, doing that kind of work, because I just figured I didn't like computers. I didn't like the calculations being done with a machine. So I just started thinking about them and said, well, how do you do it quickly without one? And so if you want to learn how to do that, look at the zeros and ones video. You can do it for exponentials, sinusoids, quadratics, cubics, you name it. You can work with it quickly and easily. All right, here's your first derivative, x cubed plus 2x minus 5. Very similar to the first problem. To find y, we're going to integrate x to the 4 over 4 plus x squared minus 5x plus c, and then we're going to let c equal 7. There. Solving differential equations after 2 weeks of working with calculus. That's pretty good. Let's get that out of the way. Another differential equation. Division becomes multiplication, so y dy, separation of variables, 2x dx. We know this is going to be x squared plus c, and I'm going to get a c out of this one as well, but I'll move it to the right, and so that's my first step. 0 gets me 8, so I might as well throw 8 in right now. 64 divided by 2, 32, that's a 0, so c's 32. So what were you looking at? You were looking at multiply everything by 2. Y squared minus x squared equals 64. You're looking at hyperbola. Not that we do a whole lot of work with those anymore. We very rarely get to study them as much as we probably could at the Algebra 2 level, unfortunately. But so you look at the original problem, maybe you put that in your memory banks and go, geez, I'm looking at a conic section. All right, so that one's done. Most of these problems you can do in 20 seconds or less with enough practice. I'm starting to get enough practice back because it's been a while since I've done these. So x squared y, done that for 2 weeks now, so I know the answer to that one is 7e to the x to the 3 over 3. Let's find out y. Multiplication by y becomes division by y, and another way of writing dy over y is 1 over y dy. So I'll be using that right now. X squared dx is on that side, so I've got to integrate x squared dx, and that becomes x to the 3 over 3 plus c. So this becomes x to the 3 over 3 plus c, and now I can see that this is 1 over y on this side. So if I integrate, I get the ln of the absolute value of y equals x to the 3 over 3 plus c. I do e to the on both sides, although the inverse of ln is e, but this one in particular is going to take a plus minus, and it's going to be e to the x to the 3 over 3 plus c. Pretty soon I'm going to stop writing that, and I'm going to cut to the chase, because we've already talked about this as being e to the x to the 3 over 3 times e to the c. That's when you add exponents, right? M squared times m to the third is m to the 2 plus 3, a little algebra review. So what do we call e to the c? And I'm on the positive side. 0 gets me, 0 gets me 7. So I'm just going to write plus minus e to the c. I'm calling a. E to the 0 is 1. So therefore, that's a 7. Now, as we keep doing this level of difficulty, we don't have to do any work 2 or 3 weeks from now. Just write your answer. And we'll do some other ones like it along the way. So here's big F. I want to know when it's concave up. If I give you a little f, is x plus 3 times x minus 4 times x plus 1. So we're working with the first derivative. That's the first derivative. When it's concave up, do you remember now? Have you heard it enough times? When the first derivative is doing what? The parent function is concave up. When the first derivative is increasing. So we want to be able to plot that. There's your Algebra 1, Algebra 2 skills. We have roots at -3. I put a dash there because it's for the first power. At +4, I put a dash because it's to the first power. This is an even exponent, so at -1, we're not going to get a change in sign. Right? If I put in -2 or if I put in 0. It doesn't matter. When I put negative 2 or 0 in, that's still negative. When I put negative 2 or 0 in, that's still positive. And it doesn't change signs here. So, if I put a big number in, I'm heading to positive infinity, polynomial with a linear, then a quadratic looking vertex kind of look, and then another linear. All right, so when am I increasing? Well, I can't answer my own question because I don't know that value. Okay, so let's call this the second derivative now. New question. All right, when using the second derivative, little f prime is the second derivative of f. So how do I tell about concavity with the second derivative? When is it concave up? Parent function. When the graph is positive. That one I can nail. From negative infinity to negative 3, right to there, this graph is positive. So big F is concave up from negative infinity to negative 3, and I'm not including negative 3. And then I'm positive again over here, starting at 4. So union 4 to infinity. All right, so there was a little bit of practice. And now we'll look at integration if given a graph. Interpreting a graph, which is really the same kind of questions I just asked you a second ago. Except we'll be looking at the graph and answering our questions based on what we see, provided we are able to make a connection here. And let's see if you can make that connection yet. You haven't seen this too much. I think the first one we did was Calc 10, lesson set 10. But I plan on doing them every even lesson set now. All right, so got a bunch of questions, and I'll find where I can position this board so that hopefully we're not in the fog, which is over on the bottom right-hand part of this screen. I think that's going to work. All right, so I'm giving you as an initial condition, starting to think about, yeah, that's plenty. So big F of x is from 2 to x, the graph of g with dummy variables. So here's g. And I want you to answer the following questions. What is big F of 3? Okay, big F of 3, and 3 is an x value. So I guess we're integrating this from 2 to 3. So that really questions whether or not you are conceptually understanding what integration finds. Area under a curve. Well, we got a curve, and I got area from 2 to 3. I think I've got a rectangle, and most of high school math deals with rectangles. So I've got a width of 1 and a height of 2, so that's 2 units of accumulation. Oh God, yeah, I did this before and I didn't think I had the volume on. So I got to erase this stuff because you had some answers there. Don't cheat now. Don't go look at those answers. Think about the problems. At least think about them. You don't have to think about them long. If you're not sure what to do, then the first stage of learning is following. So after 10 or 20 seconds, I encourage you to go, oh, let me just look at it. Come back. You're going to get the same questions again. So F of 3 is 2. And when you look at something like this, you should have a feeling for what if x was to equal 2? Remember, you're pausing the video every time I ask a question. Well, I hope you'd say, no area accumulation. I'm not accumulating area to the right. There is none. So big F of 2 is 0. Okay, I must have done that before when I didn't think the volume was working. Okay, so I'm going to leave this dotted line. How about big F of negative 4? Well, that's how does area accumulate if we look in this direction. Well, each of those arrows is negative, so the widths are negative. Widths are negative. And initially, my heights, as I look to the left for 0 to 2, those heights are positive. So I have a negative and a positive height, which means a negative times a positive means that I'm actually going backwards on my graph. 2 units of width, 2 units cut in half, minus 2 units of accumulation. That means whatever my graph looks like, 0 is going to be 2 units higher than big F of 2. Big F of 0 is going to be 2 units higher. And now my altitudes are also negative here, so I'm actually accumulating positive area with respect to, I'm adding positive amounts to where I started from. Okay, now I've got 4 units. 4 by 4 is 16 cut in half. This is 8 units of positive area. So it looks like F of negative 4, if I've done it properly, let me just check, 2 times negative 4, okay, negative 2 times negative 4, positive 8 cut in half is 4 and 4. Yeah, I believe that's true. I believe that is correct. Now, what's little f? Well, you got to look at this, and you got to say, can I figure out what little f is? Well, we can take the long route, and the long route is to integrate little g, which gets me big G of m, from 2 to x. Well, that becomes big G of x minus big G of 2. And if I take that derivative, I get little g, which is this graph. And the derivative of this, I think I should have written this a little lower so it doesn't look like an exponent. Big G of x minus big G of 2. So g of x is the derivative. Little g of x is the derivative, and this is the graph of g. And I'm asking, what is little f of negative 2? Well, little f of negative 2 is the same thing as little g of negative 2, which we are going to look at the graph. Here's negative 2. What is g of negative 2? Negative 4. Now, if I didn't want to do all this work on the right, then I can take the shortcut, which is drop x into the parentheses, which gives me little g of x, multiplied times the derivative of x, which is 1, minus the little g of 2 times the derivative of 2, which is 0. And we can see that we make the connection that little f of x is the graph that we're looking at. All right, so let's clean that up a little and continue to ask a few more questions. Okay. Big F of x. I must have asked a question. Why don't I ask, when is big F of x decreasing? When is big F of x decreasing? Well, I need the derivative of big F, which happens to be this graph. And it's a first derivative. Right? We made that connection. The connection should be written, probably, if you're taking a college board test, it probably wants you to make sure you say somewhere that little f of x equals g of x. Probably have to make that connection. And so, when is big F decreasing? When little g of x is less than 0. Well, that's negative 4 to 0. All of these are y values that are negative. So negative 4 to 0. Why don't I do it as an x equals? I got to be less than 0 and bigger than negative 4. And that answers the question, when is big F decreasing? F prime at 1. Little f prime at 1. Well, that's the rate of change of this function. At 1. Well, I can see I go over 2 and up 2, so I'm going up at 1 to 1. Think of that as acceleration. Might be nice to graph what we think big F looks like. Might be good for you to do it maybe at the beginning of the problem. Might be easier for your brain to process this stuff. So what's happening here? This is the slope of tangents, and I'm starting with a slope at 0. Maybe I'm going to negative 4. Maybe halfway between is negative 2. So a slope of 0 is flat. Negative 2 is going down. Negative 4 is going down faster. That's where I'm going down fastest. I'm going down at 4 to 1. And then I'm going down at 2 to 1. And then back to 0. So then I'm going back to 2 to 1. And then to 0. And then I'm increasing because my first derivative are positive values here. So I'm going up at 2 to 1 at some point. And then I'm going up at a constant rate of 2 to 1. Okay, so that's what my graph looks like. And so I'm looking at, I guess, when is it concave up? Because I did some erasing here. So when is big of X concave up? Well, it looks like it's concave up from here to here. Now, what's your graph doing from this value? And that value was -2, and this value was +2. Will you tell me what this graph's doing from -2, which is that y value, to this y value? Looks like the first derivative is increasing, and it looks like it matches up with concave up. So what's the equation of line tangent to big F of 4? Well, I can write x minus 4, and then I got to figure out what the accumulation area is here. It's one big rectangle with a width of 2 and a height of 2, so that's also 4. And I need the slope. Well, this is telling me the slopes. What's that slope? It's this y value, which is 2. And then I started to look at derivatives from a graphical perspective. All right, so let's hope that this is a little more easily seen and heard. And if so, well, we'll live with it. And then if I can figure out how to change the order of, I've done about 520 videos, then I would order them probably from an Algebra 1 to a calculus perspective. And I think probably if you're doing calc and you haven't looked at the video, the relationship between integration and differentiation, I highly encourage it. If you haven't looked at integration from a geometric perspective, go to the playlist and look at that. And if you're having trouble with the foundation, go back to the 50 lesson sets, the Algebra 1 through, and figure out where you're at, and then do a bunch more. All right, and within a week or two, you can get through all of that stuff, and I'll probably be ready to tackle some of these concepts. All right, rambled a lot. Let's hope that you can see this video a little more easily, and thanks to John, I don't know your name, but thank you for making the comment, because it's pushing me, I think, in a better direction. But yeah, I'm a dinosaur, so I'm probably not going to go out and purchase a lot of material, because probably when I'm done with these lesson sets, I'm probably done. I don't know if I have anything else to offer. But you never know, because when you keep doing things like this, things come into view. All right, good luck.